Dominic Chang the AstroAI talk. Dominic's a grad student at Harvard Physics, and he's an associate of the Black Hole Initiative, and he's been working with images from the Event Horizon Telescope, and he works on a number of topics for physical interpretations of the images and approximations to it. And today he's going to be telling us about Bayesian black hole photogrammetry. Dominic, we're happy to have you. The floor is yours. I'll just remind the audience and you that this is intended to be a very interactive session, so please feel free to interact with questions. And also feel free, Dominic, to pause and check on people if you have questions for them or whatever. But other than that, the floor is yours. Thank you.
All right, thank you. Okay, good. So everybody can hear me, that's good. So I'm talking about this project that was recently accepted into AppJ. So it's called Bayesian black hole photogrammetry. So it's called Bayesian black hole photogrammetry. And it's essentially what the description was, right? So the goal, I'm a part of the EHT, the Event Horizon Telescope. We took data, and we took the first picture of the event horizon, or of the shadow of a supermassive black hole, and the question is like, what kind of sensor can do? Okay, so the starting point is M87. So M87 has been studied for a long period of time. It's been observed at many wavelengths, ranging from the gamma rays all the way to radio wavelengths. And depending on the wavelength that you observe M87 at, you see different scale structure. So if you start at the gamma rays, you start to see emission coming from the jet. And then once you get all the way down to the radio, there's this scale similarity that happens. So as you increase your wavelengths, you start to zoom in closer and closer, and you see this long linear feature, which is a jet of M87, but it looks the same for a while as you're zooming in. But after a while, after some period of decreasing your frequency, eventually you get to EHT wavelengths, at which point you can.
Sharing your screen, because I don't think some people are seeing it.
Are they seeing my screen now?
Now it's better.
Okay. Yeah, so eventually, so let me start back. So this is an image of M87. This is sort of depicting M87 observed at many wavelengths. And this is from the multi-wavelength group of the EHT. So it's a nice summary of the different observations of M87 that you can see. So the point being is that eventually you get to the EHT wavelengths at which you can see the shadow of M87, and this is depicting the near horizon. This is really the near horizon physics of M87. So the question is, I know that we're at this regime where we can see the near horizon physics of M87. What science can be done on this? So first, let me talk about some of the previous science done on M87, particularly some of the previous measurements. Focusing here on the mass measurements, I've labeled various different measurements that are done in the past and are available in literature, and they typically fall within two categories of measurement. They're both tend to look at the spectra that's coming in from the bulge region of the galaxy that's within the sphere of influence of the supermassive black hole, and typically they model the spectra due to the contribution from dynamics from either stellar dynamics or gas dynamics. So I colored the stellar dynamics measurements in green here, and the stellar dynamics measurements in blue here, and the gas dynamics in green. And what you typically see is that the gas dynamics will model a mass that's smaller than the stellar dynamics, usually by a factor of 2 or so, even up to a factor of 3, as of recent. In black here is the EHT measurement, and you can see that the EHT measurement is consistent at least mostly with the stellar dynamics measurement. There are other measurements that have been done in the past, include measurements of the inclination of M87. So so there's a jet that I showed before that we've observed before, and there's a near horizon spin. And we haven't been able to constrain the spin axis in the past, but we have been able to constrain the jet axis in the past. And in particular, we see the jet axis typically lies at the inclination of roughly 18 degrees. Sorry, I think I have more feedback.
Is your computer muted?
Yeah.
It's close to the.
Oh, it's turning down, maybe? Maybe you're supposed to, yeah.
Oh,
Maybe there's a volume in
it
the.
might have been, is this better?
Yeah.
Yeah. Okay. Yeah, so typically you see a large scale, you measure the large scale jet inclination in the past through Doppler effects. You can constrain that to be roughly around 18 degrees plus or minus 2 degrees, so. Moreover, you can just look at images of 87 and see the alignment of the large scale jet. It points somewhere with a position of angle of a PA of roughly pointing to the west, to the southwest. And but the other things about MH7 you want to constrain are things like the spin, and that is something that has traditionally been very hard to access. More recent measurements of M87, things like observations of a large-scale jet over long periods of time seem to indicate that the jet could be precessing, and this could be an indication that the spin axis of M87 is possibly misaligned with the large-scale jet axis. So given that we have access to this near horizon physics, can we measure these parameters? Can we find out information about the black hole parameters that may or may not be consistent with the large scale information that we're getting from the jet? So first, let me talk about the EHT. So what the EHT is a global VLBI array that's very long baseline interferometry. In 2017, when these observations in MH7 were done, it had 7 sites. It has sparse coverage in the UV domain. And in particular, the largest UV distance that's seen by the array is roughly the size of the Earth. And that gives you roughly 8 gigalambdas in the UV distance. So what this means for observations is a sparse array. So typically, if you imagine you had a telescope at every point on Earth, just sitting there, and you looked at M87, you get a very crisp image. M87 is roughly the size, the Earth is roughly the size necessary in order to observe M87, but we don't have a telescope sitting everywhere on Earth, so instead what we have is a sparse array. So it really looks something more like this, where you just have a sample of the UV points of visibility data at each UV point. And I'm not sure I don't think it's coming up very clearly on the screen, but what happens when you have a sparse sampling is that when you take the Fourier transform of that to get an image, you get what's called a dirty image. So it doesn't really look like anything. It just looks like a mess, essentially. But essentially what you want to do is that you want to get from the sparse array to the image. And in order to do that, you need to make some sort of assumptions. You need to characterize your solution space in such a way that you can essentially remove the fictitious solutions that aren't real in order to get to the true image. And usually that's done by marginalizing on some sort of assumptions. That requires some sort of model in order to do that. Usually the model is how you impart these assumptions. So traditionally in EHT, there are 2 methods that are typically used. They fall into these broad categories of imaging and geometric modeling. They're not, these are sort of just based, there's no strict definition on what counts as imaging or geometric modeling. In fact, there's a very broad gray line there between the 2, I'd say. But typically the features of imaging are such that the models are just very flexible. So you typically think of imaging models as these extremely flexible things. They tend to make very, very few assumptions, as little assumptions as possible. In particular, for the 2017 analysis, the imaging models were just essentially, you assume they were just a collection of pixels. The pixels need to be positive definite, so you can't have negative intensity. And they're constrained in certain ways. So for example, they're regularized to have total flux equal to the observed flux of the image. They have relative entropy regularizers or the L1 regularizers to ensure that this image was not too sparse, a total variation regularizers. So this is very typical of whenever you have an ill-posed problem, you have to induce some sort of regularization in order to get the solution that works, that makes sense. But whenever you take this approach, the result is that you end up making typically weaker conclusions. Like at the end of the day, you just get an image. You can clearly make some conclusions from this image. Like we look at it, we see these different methods. They all have a dark central depression. They have a ring, so we can say from the imaging methods that we see a ring, for example. But if you want to make stronger conclusions, like if you want to say measure the diameter of the ring, measure the image asymmetry of the ring, or so on, there needs to be some post imaging analysis that's done. So another approach is geometric modeling. These typically make stronger assumptions. And because of that, you're able to get stronger conclusions out. So for example, you can design your model. Like if you know you're looking at a ring, you can design your model to be a ring, fit that ring to the data, and then thus immediately back out something like a ring diameter or a ring asymmetry. But the problem with geometric modeling, at least the way that we do it, is that it's only really fits image features. So it's very good for describing features of the images, but it's very not. It's getting louder.
Maybe there's a volume there.
Yeah. Okay.
Yeah, you should have a volume thingy on the box, but it's fine.
Okay, yeah, so it's suited for measuring features of the images, but not very well suited for measuring features of the source. So typically, again, if you want to measure things like the mass or the inclination or spin axis position, in order to do that, you again have to do some sort of post-analysis modeling on this. So, but just as an example, I think this was a video that was supposed to play. It's not playing for some reason. Yeah, so just as an example, this is a fit of various geometric models to the 2018 M87 results actually. And you can see that you can take different classes of models and ask questions like, oh, which model best fits the data or best describes the data. And just as an example, I shown their several Gaussians. Like I just took a toy example where I just threw several Gaussians at the data, and you can see that they like to arrange themselves in a ring. So this helps to give you support that the feature that you're looking at really is a ring. And then once you do fit a ring, it allows us to back out information like the diameter and ring features like I previously stated. But the thing is that can we do better than this?
Sorry, so you're saying you use both, you first try to figure out.
And so this is not the one where you're assuming is a ring, if you had put Gaussians, right?
Yeah, I didn't, if you put down Gaussians, I'm not assuming a ring.
So can you do both, like first not assume it's a ring and make sure it's a ring, and then use the one that you fit a ring and get the parameters?
Yeah, so indeed that's something you can do. So I'll mention it a little bit later, but one of the reasons we do something like this is because geometric modeling is so constraining. If you fit a ring, then you can't say anything about it not being a ring. So we fit models that aren't rings and models that are rings. And then we're able to determine the support of the models being rings and versus the support of models not being rings. And use that to come to a conclusion of whether what we're looking at really is a ring or not. Yeah. Okay, so can we do better? So the best simulations that we have are of supermassive black holes, assuming that what we're looking at is a supermassive black hole. Are these things called general relativistic magnetohydrodynamics. I've shown some images of GRMHD here just for an example. So on the top we have some mad simulations of various spins and accretion parameters. And on the bottom we have same simulations again of various spins and accretion parameters. And the left shows the images. Sorry, the left shows the images, but on the right, what you see instead are the sort of the bulk emissions. So where in the 3D geometry that emission is coming from that gives rise to those emissions. And these images are to show, these images sort of represent what you typically see in GRMHD, at least on an average level. And one thing that you can see is that you typically see emission that pops up. Let's see if this works. Yes, you typically see emission that pops up around this this disc-like feature, or this like Pac-Man shaped feature. And this is the photon shell of the black hole. So this is this unstable orbit region around the black hole. You typically see peak emission coming from around there. And moreover, the peak emission that you typically see tends to have some scale height to it. So this is interesting because many models of black holes out there tend to assume equatorial emission. But even in GRMHD, which which are our most accurate simulations out there, you can see that the disks can have a very significant off-equatorial component to them. So these are essentially the conclusions that we take from this, from just looking at these GRMHD solutions. So all the models have this non-negligible scale height. The same model, so these two models on the bottom tend to have significantly more scale height to them than these MAD models, but nonetheless, there's some non-negligible scale height to them all. And the scale height that you observe or the emission, the location that you observe tends to depend on the electron temperature models that you put into the model. So what that means is that if you want to sort of invoke these properties into any model that you're coming up with, it needs to be fairly flexible. But one benefit that we do have is that the emission tends to be compact. So it tends to be consistent with this photon ring region, which actually helps with impose a strong power on the kind of models we're going to define.
Sorry to interrupt you,
Yeah.
but I have another quick question. So
The MAD models include magnetic fields in the same zone.
Yeah, no, the MAD models have strong magnetic fields and the same instead have weaker magnetic fields is really what it is. Yeah.
So they're still accurate.
Yeah,
Okay, so you think the magnetic fields help keep the disk more equatorial? Is that how it looks like?
so what it is that the magnetic fields sort of push the disk out. So the jet in the MAD models tend to be more powerful and larger. So what happens is that what the current belief is that the region that's lit up is a jet wall. So the jet is really like curving in this parabolic way out here for the MAD models. And because it's pushed out in a parabolic way, it tends to flatten the emission region. But with the same models, they have a much thinner disk. A much thinner jet. So the jet is more like this. And that's why you get more emission coming off the equatorial plane. That's the interpretation. Yeah. Okay, so in with that in mind, come up with a stupid model. It's a very simple model. It's not stupid, but you know, it's the first thing you can think of. Instead of having an equatorial disk, we have cones, and a cone is kind of nice because if you take a cone of pi/2 opening angle, it becomes a disk. So it's kind of a nice extension to the typical equatorial models that people use. So we propose this simple conical model. Essentially, what it is that you have emission that's coming from these two cones around the black hole, again, to mimic what we see in GRMHD. This is essentially the power of GRMHD being imparted into our model. The fluid is constrained to flow within the cones. The magnetic fields can thread orthogonally to the cones or along the cones if they want. It's allowed to orient freely. We ray trace this emission, and we include sub-images. So we include so the image of a black hole will be comprised of multiple sub-images, depending on whether light wraps around the black hole 0 time, 1 time, or 2 times, or so on. So we just ray trace that to get an image that's comprised of all the sub-images, and that gives us something that looks like this that we have up here. This model is fairly simple. It ends up just being a 13-parameter model that describes the entire thing. In particular, the black hole, there's just essentially 3 black hole parameters, maybe 4 if you include the position angle and where it's pointing, and the rest are just accretion physics. So the accretion physics is really simple. And the further assumption that we make, of course, is that the model is axisymmetric. So we don't have to care about positional variability in the model, spatial variability in the model. And one of the benefits of doing it this way is that the model is really, really fast. So typically when you do GRMHD, a single simulation can take months to run, especially since you have to wait for it to run and equilibrate over time, and the equilibration rate takes a long time. If you have a model like this, you can just fire it up, get an image, generate images real time, play with the parameters, see how they affect the images. It's really very convenient for understanding what parameters affect the image in what way. And this is just a plug. So all of this is available in this ray tracing code I wrote. It's called Krang for Kerr Ray Tracer for Analytic Null Geodesics. The code is open source. It's available on GitHub. It's currently under review for a JOS paper. So you know, if anyone is interested in using it or wants to talk to me about it, wants to add features, please go ahead. Okay, sorry, were you trying to get the
I wanted to know how far along you are with adding the polarization to this.
Oh, so this, I guess I should have, yes, this model is already polarized. I just don't fit polarization in the study. Because in designing this model, I assume all the emission is optically thin, is Faraday thin, but Faraday effects are very important for polarization. So I think even though the model is polarized, fitting it would give biased answers. I just purposely don't fit it. But the model is polarized as is.
And just to conclude, how hard would that be to add to fit for polarization? Because EHD images are nicely fully polarized, so you're throwing away 3 more information, right?
Yeah, but
that you could just add them.
it's not hard to fit for it, but it would. I'm missing physics for the polarization, so it would just give biased results. And so basically, in throwing away the polarization, I'm paying the price for having wider posteriors, so just having bigger errors, of course. I could fit
Just read the last question,
Yeah.
but you know that simple ring model in a paper that you wrote and you're part of it?
Yeah.
Even single ring model without cone works actually for reproduce. Of course, you have to tune them and so on, but it's not that. I don't know what do you mean by missing physics.
So by missing physics, I mean the Faraday effects, and in that paper that we wrote, we fit time average GRMHD. So this model is designed to fit data, and data is more representative, like a snapshot of GRMHD. So this model is already misspecified for that aspect. And if I'm fitting again even further misspecified model to data, it will bias the results even more. So I just don't fit it. Yeah.
I think I just missed something of the model. Could you go back a little bit to say how this model, like, what is the model?
Oh yeah, so the model is really, so the model is a combination of an emission model and just a ray trace that emission model under the assumption of a curved geometry. So I assume a curved black hole, and by assuming a curved black hole, what that is doing is just defining the way how I ray trace a model. So essentially the ray tracing code depends on things like the black hole spin, it depends on observer inclination, and it depends on the position angle of the spin axis. So by just calling it a curved black hole just means I'm going to ray trace the emission under the assumption that the space-time is curved, and of course I'm going to use the local physics associated with curves. I'm going to project down to local coordinates that are consistent with the curve solution and do everything in a like general relativistic way so that everything makes sense.
So that before you do that, you need to have a solution to it. Is that a GRMHD solution that you're retracing, or
So
how do you get around the GRMHD?
So instead of a GRMHD, I replace a GRMHD with a simple emission model. So the emission model is of just some fluid that's constrained to lie in a cone, and it's embedded in a magnetic field. And the fluid is taken to be axisymmetric, and the magnetic field is taken to be axisymmetric.
So what you take from the GRMHD solutions is that you have a cone typically, like you take the shape of the solution and then you embed it in a curved space-time onto the ray tracing.
Yeah, essentially.
So may I have one last question? Actually, like follow up to what Cecilia said. Yeah, so I mean, it's really amazing, but I think that we can be a little bit more promised. You know, about this, the fact is that we can take advantage of geometry simulations and everything. And in fact, those optical depths and so on, maybe you can come up with some analytical forms when you change the magnetic field strength and so on and so forth, and then plugging back this analytical or semi-analytical hyper-dimension of this into your model, and then there will not be any biases. It's kind of like a calibration, like alpha calibration that people normally do. So maybe we should definitely talk, but does that make sense to you that you just need some modules for optical depth? So
yeah, essentially, so I guess you're correct. So the Daniel Colombo, who's one of the co-authors of this paper, has been exploring that. I'll add some so there were some additional difficulties for why polarization is not included here. One of the reasons is that when you incorporate polarization, there's optical depth, right? And the optical depth implies that there's depth to the emission. But because I've assumed that the emission lies on the cone, it's effectively two-dimensional. What that means is that you have to come up with some sort of way of defining the 3D structure of the cone, given that it's two-dimensional. And the way how you do that is not well defined, and it just was not within the scope of this project. So, but that is something that we're exploring. Yeah. Okay, so, yeah, so now that we have this model, of course, the question is like, does it look like GRMHD? And this plot here is kind of a busy plot, but essentially what this is just to show is we have time average GRMHD on the top row. I put the parameters here that describe the time average GRMHD. So in particular, we have the mass. The mass here is a theta G parameter. This was a simulation of Sagittarius star. The spin here is shown as this A parameter, so this is 0.9894, and the inclination is this theta naught parameter, so this is like 30 degrees, it's 50 degrees, 70 degrees, and 90 degrees. So we have this essentially the same geometry simulation that's viewed at increasing angles. Here I have an equatorial model, which is essentially just the dual cone model, but with the opening angles fixed to pi/2. Typically, people model sources as just equatorial model, so that's just to see whether it's good enough. I have the dual cone model, and I have the as a combination model. So one way you can think of this is that this is like a 1-zone model, it's like a 2-zone model, it's like a 3-zone model. There's just more parameters that contribute to the emission. And one thing that you can see is that at low inclinations, 30 degrees is not the lowest, but it's kind of low enough. And even at moderate inclinations, even the equatorial model does fairly well. And so I should emphasize, so what I'm doing here is that I'm fitting images of the model to images of GRMHD. So I just do essentially like a differential evolution algorithm and just run it for 100,000 steps and just take the best fit. And what you can see is that, so there's no error bars in this, it's just a simple optimization.
Wait, so you're doing GRMHD for some steps with the initial condition being your dual model?
No, so I take a GRMHD image and I fit my model to the GRMHD image. So I just like there's some prior range, the image initializes somewhere randomly. I do optimization of the image to the images of GRMHD by minimizing the cross correlation, the normalized cross correlation between the two images. And then I just, after doing that, I just read off the parameters that the models assume to get to minimize that normalized cross correlation. And what you see from that is not only do the models essentially reproduce the image, but they reproduce the image with fairly accurate parameters. So you can see here, for example, this equatorial model infers an inclination 27 degrees, that's only 3 degrees off from the truth. The mass is the same, and the spin is roughly the same. And likewise, for the dual cone and equatorial dual cone model. And what generally happens is that as you increase the number of emission surfaces, there tends to be an improvement in the fit, in the inferred parameters, but the dual cone tends to be good enough, at least for our sources. At this 90 degrees inclination for Sagittarius star has been ruled out, for example. The models don't perform very well at this inclination, but this is likely not our reality. So what the conclusion from this is that likely this this dual cone model is good enough for fitting to data, to EHD data. The benefit of doing a study like this as well is that since I'm fitting to images, it's essentially like I'm having the true resolution. This is like how the model would perform if you had true resolution, like a fully completed VLBI array. Oh, I think there are questions. Oh, I did not. Yeah, okay. And of course,
Oh, sorry.
yeah.
I thought it was on Zoom.
We have do you have a general intuition on why the model performs a bit worse at like closer to edge on inclination? Does it have to do with the asymmetry?
Oh, why it performs more poorly? I think it's
a general intuition.
Yeah, it's really so, you know, sort of saying model misspecification is kind of it definitely is model misspecification. You can see it here. So what happens is that I mentioned before that the jet is kind of parabolic in nature, and I've assumed that the cones are just flat. So the thing is that if you look at a parabola face on, it's indistinguishable from if you're looking at the cone face on, but if you look at the edge on, it's very obvious. So that's just a model misspecification showing up here. You can see that essentially a cone is a bad description of the side view of a parabola, but it's a good description of the face on view of a parabola. That's essentially what it is.
Got it, thanks.
Yeah. If you're wondering why I used a cone instead of a parabola, it's just because the mathematics turns just work out such that the cone is very easy to model instead of a parabola. This is essentially just to show that the images look very similar. So this is the dual cone model fit to the GRMHD, and you can see that their emission profiles overlap by quite a bit. This is a percentage residual difference. We get a maximum of 30%. I think this is a little bit. I think this sort of understates actually its performance, because you're getting 30% here because the emission is peaked at this region. So it goes up to infinity. So a small difference will cause a large percentage difference. So it makes sense why most of the difference is really on this photon ring region. But one thing that you see is that once you blur it to this is actually below nominal EHD resolution. Once you blur it to 10 microarc seconds, the nominal EHD resolution is about 20 microarc seconds, you get much better agreement, with the residual percentage difference shrinking down to a peak of 6%. Now, on to sort of one of the key words in the paper, photogrammetry. So I don't know if anyone's familiar with this word. So what it is this process of studying sort of 3D geometry of objects from their images. So typically when you do photogrammetry, you look at some structure like this owl, and you take images from multiple angles, and you have some model of the structure, and you can use those angles to constrain information about the 3D geometry. So the goal here is to do something like this with the black hole. And this is not a new idea. This has been done before. So for example, Aviad Lewis had this essentially like a nerf, like a neural radius field that he fit to EHD data to infer the 3D accretion flow from around Sagittarius star, and this sort of indicating that something like this is possible. But when the EHD produced a single image, typically when you do photogrammetry, you need multiple images. So like, why does something like this even work in the first place? And I think, at least for my model, the main reason that this works is because as I mentioned before, we ray trace multiple images. A given image that you see from a black hole is not really a single image, it's a sum of multiple images. So even though you have a single image, and it is comprised of many sub-images where you see the source from multiple angles. So that this actually enables photogrammetry to be possible. So this plot is just showing essentially that photogrammetry study where I fit, again, my model to GRMHD, this time GRMHD is of M87, and then after fitting the images, I ask, where is a 3D emission from around the black hole coming from? So again, you can see that the model does a fairly good job of reproducing the true parameters from the GRMHD. So you see, for example, the true inclination here is 17 degrees, it fits 19 degrees, the spin is 0.94, it fits 0.89. But here you start to see where the equatorial model starts to fail. So particularly in the same simulation. So this is that same simulation that had very large scale height that I showed before. It has this weird ring topology, this weird double ring topology, and the equatorial models are unable to reproduce that double ring topology. But here you see the dual cone models are successfully able to get that. Moreover, if you ask the models, where is the 3D emission coming from? So here I've colored the emission coming from the cones in red and the equatorial one in orange, and you can see that the conical model is able to reproduce emission that's consistent with the true GRMHD in gray. So the models are able to somewhat infer. I mean, it's not exact, but they're fairly consistent with where the true emission is. In fact, and promisingly enough, they get that the emission is compact. They get that it's compact within the photon ring, and they get the scale height roughly correct. And again, just plugging my code. One of the improvements that this model has over doing something like what Aviad did is that Aviad's ray tracing Aviad's ray tracing essentially was not differentiable. One could not back propagate through it. So I think this is more useful for you folk here since you're interested in AI. So if you want to say ray trace an emission model that's like a neural net, you're able to do this with my code because this code is automatically differentiable, and you can essentially treat it like a ray tracing layer on top of a neural network. So in particular, you can use that to do studies like this, which I've shown here, where essentially if you're asking the question like, what features in the image are influenced by what parameters of the emission model, that this allows you to answer that, where here I just essentially just show the magnitude of the derivatives of each pixel with each model parameter. And one thing you can see is that the photon ring, for example, is the most sensitive to changes in the mass. And it's also most sensitive to changes in the spin and most sensitive to changes in inclination, which makes sense because you always hear this story that the photon ring is insensitive to astrophysics, and that is really what's encoding the black hole gravity parameter. Of course, if you look at, and this is also, you also see this happening here when you take the derivative of pixels with respect to emission parameters, you see things like the n=0 emission, most light lighting up, or both emission lighting up. Yeah, any questions on this plot?
So when you talk about the three-dimensional reconstruction, with those emissions, like you plot in the last slide, isn't it true that we azimutally average them and time average them? So it's kind of like it's still two-dimensional to me.
Yeah,
right?
that is true. So this is, so essentially what I'm saying, I'm proposing this as a model for time average and azimuthally average GRMHD. So you're correct. I'm not claiming that this is a representation of a snapshot, which is why I was sort of saying earlier that I didn't want to just go off and fit polarization because there are various things that are misspecified in this model, which I think adding the polarization will further confound.
But what I think is truly three-dimensional, because I think that they were also working on the velocity fields in the 3D that you are not here, right?
So this has velocity fields, but it assumes axisymmetry. Aviad's is truly three-dimensional.
Okay.
Yeah. Okay, so
Just one more question. Very fascinated by the differentiable ones that you mentioned, which kind of looks like some sort of saliency mapping in AI. I'm just curious if that method can be used to infer like a photon ring from the HD image, even though we still doesn't have the resolution to see the photon ring.
I guess it doesn't immediately come to mind how you would use it for that, but maybe. I suppose like maybe if you see what directions in parameter space are most sensitive to changes in the EHT image, then you could say like, oh, you know, the black hole parameters are most sensitive to changes in these pixels in the EHT image, so that might imply that you're sort of you're sensitive to the photon ring. So maybe there's something there. The immediate way to do that doesn't come to mind. Yeah.
Thank you.
Yeah, okay. And additionally, it's also GPU compatible. You can run this on the Mac. So it's really hard to get this running on the Mac because it had to be type stable and type preserving because the Mac does not support Float64. But you can also run it on CUDA. CUDA supports Float64. That's completely fine. It's very portable. I've run this in HPC environments. So this is a very flexible model. You can plug a neural. I'll share an example later where I plug a neural network into it. So on to the next top point in that title, so the Bayesian part. Okay, so if I don't know how many people are familiar with Bayesian statistics, but Bayesian statistics is really simple. It just boils down to the Bayes theorem, and all that is saying is that the probability of the model given the data is equal to the probability of the data given the model, and the probability of the model divided by the probability of the data. That's all it says. There's nothing fancy there. But sort of evaluating this problem ends up being hard, even though the statement itself is really simple. Each term in this statement has a name. So the probability of the model given the data is called the posterior. Probability of the data given the model is called the likelihood. Probability of the model is called the prior. So remember before I mentioned that we invoke our prior information into the model design. And then the probability of the data is called the marginalized likelihood. This term ends up usually not being that important when you're actually doing a Bayesian analysis, just because you only care about relative probabilities. So the actual normalization is not important. For AI usage, essentially the likelihood is just a loss. So if you want to plug in a neural net, you just take the likelihood and use that as your loss function. Okay, and doing Bayesian analysis is kind of beneficial because this goes on to Celia's question earlier. It allows you to do things like Bayesian model comparison. So like, let's say you fit the data and you fit the data with a bunch of geometric models. Some are ring-like, some are not ring-like, and you want to know, does the model prefer, or does the data prefer models that are ring-like versus non-ring-like? You can do that by comparing things like the model evidence between different models. And by marginalizing over that, you can make plots like this, where essentially you know, after classifying the models as Gaussian-like or ring-like, you see that there tends to be a preference. The data tends to prefer these ring-like models. In particular, this is coming from the 2017 paper. We did a similar thing in 2018, and we showed that the data broadly prefers ring-like models over non-ring-like models.
What are these two down there? Do you know? Is it like the rings are?
Oh, this is just a circular Gaussian, and this
I
is.
mean, the green ones that are much lower.
Oh, I think it's just
That makes it less likely, or?
this is a top hat. So this is a top hat. So just sort of low emission and then big emission. So it's like, and then the top hat disk is essentially the top hat that you punched out in the middle of it. So just a flat disk.
Okay.
Yeah, a flat annual. Sorry. Yeah. Yes. You know, the other thing that's important is this loss function or the likelihood. So in particular for our analysis, we construct likelihoods out of what's called closure quantities. So what that is, I mentioned before that EHE does not observe the pixels, observes visibilities. So visibilities are really just the Fourier transform of your pixel intensity. So you have a pixel intensity, you do a Fourier transform in the 2D plane, you get the visibility. So this script V is essentially the true visibility. But what we really see are these observed visibilities. And observed visibilities are related to the true visibilities through certain corruptions, and they get two corruptions in particular, at least in the way how we model it. One is through gain corruptions, another one is through thermal errors. The gain corruptions have a form that's sort of well understood. They tend to arrange themselves in this way. They're essentially just like some 2x2 complex matrix, and they interact with the visibilities like this. But the thing that's beneficial about visibility is that you're able to construct quantities called closure quantities, which allow you to mitigate these gain corruptions. So in particular, if you just take the visibility is just some like complex number because it lives in the complex plane. You can construct what are called closure phases and closure amplitudes out of the visibility in this way. And then that allows you to find these loss functions, which are mostly gain invariant. They're not exactly gain invariant, but they're mostly gain invariant. I mean, without including noise, they're gain invariant, but once you include errors, they're mostly gain invariant.
Sorry, can I interrupt for a sec? So you showed us that plot before that the different sort of evidence values for different models with the green points and red points.
Yeah.
Okay, so this is not, you're not actually calculating your evidence here, are you? Like the marginalized likelihood, or are you? I would think those are fairly complicated integrals. Are you just minimizing some sort of evidence low bound or?
Oh, we are, so, or we get the estimate of it. We use Monte Carlo methods or in this study, we use nested sampling. In future studies and other studies, we've used Monte Carlo methods, MCMC. But essentially, yeah, we are actually calculating this. We integrate. And actually, no, I think the 2017 was an estimate. Well, we weren't actually integrating, but in the 2018 we do integrate. I think that's what it was. In the 2018 we actually are calculated, but I think in this 2017 it was just an estimate.
Okay.
So what's the invariance again? You said in the next slide. Their invariant.
Oh, so yeah, so there's this corruption from these gain quantities. So if you construct, because the gain quantities behave in this way, what you can see is that if you plug in essentially the true visibilities into these equations, these gain quantities will cancel. So for example, this Gij, you'll get Gij Gj star, G J G K star, G K G I star, and a G, and then you take an argument of that. So they will multiply each other. Like you have a complex phase times the inverse of that complex phase, and they just cancel. So
what are they? What are their function there?
The G?
Yeah.
They're just complex 2x2 matrices.
You normally see like Vij equals Gij Gj.
So, oh, you mean like what are they physically?
Yeah.
So what it is that when you do an observation with a telescope, there you can get errors from so a translation, for example, in pixel space, like say you look at the image and you translate it, when you Fourier transform, that's just a change in phase in visibility space. So you can get these errors in pixels, like that manifest a translation from like phase corruptions in visibility space, and that can occur from things like the atmosphere, like maybe there's a cloud, well, probably not a cloud, well, yeah, maybe there's like a cloud or changes in atmosphere that causes the signal to deviate by quite a bit. Or maybe there you have two wires coming from your left polarization versus your right polarization is slightly longer than the other or something. There are various ways that error could be introduced, but when you introduce the errors at that point, they manifest in this way.
I see.
Yeah.
Okay. So these are invariant under those.
Oh, so these quantities, these loss functions are invariant under the introduction of these gain quantities. Yeah, if you just like plug in the values into them, you'll see that they cancel. Yeah.
Okay, thanks.
So if everything were perfect, psi of jk is always 0, and so you have a loss function that penalizes you if psi of jk is not 0.
Sorry, if you have, so if everything was perfect, then the you wouldn't, so we introduced Gaussian noise, and if everything was perfect, you wouldn't have to introduce Gaussian noise. So then if everything was perfect, then the loss function would this would be 0. No, actually this would not be 0. It's more of the phase error here would be 0 if everything was perfect. But the psi ijk does not depend on whether things are perfect or not. It's more of the statement. So things can be imperfect and the psi ijk will be the same. Maybe I misunderstood the question, sorry.
Okay, I see.
Yeah, so the Gij can be whatever they want, and the psi jk will remain the same.
It's invariant under gain errors.
Exactly, yes. Okay, and the last thing that's important for the Bayesian analysis of priors. So these are the priors I take for an analysis of fitting it to data. So essentially I take flat priors just because I'm fairly ignorant. I guess you can take that as you want. I take the mass range to be inclusive of the largest and smallest mass measurements that have been done in the past plus some. So the smallest mass measurement corresponds to about 2 here, and the largest one is about 6.7 here. So just make it a bit wider. It's actually quite a bit wider. I take the spin to be anywhere between -1 and 0. The reason for -1 is because we think the jet's pointed away from us. But this is essentially a complete agnostic spin domain. I take the inclination also to be fairly large, between 1 and 40 degrees. So that's like plus or minus 20 between the average, what's measured with a large scale jet. There's reasons to think that, there's no reason to think that it's too largely deviated from a large scale jet, given that the precession that we've observed in the jet is very small. The opening angle also to give it to a wide range. Position angle points to the left just because that's where the jet points, and the rest of the parameters are also taken to be wide. And yeah, this is just, sorry, I'm gonna speed through these. So this is just to show a fit of the model to one of the geometry simulations before. This is to emphasize why it's kind of important to a Bayesian analysis. In particular, if you look here on these two modes in the mass, you see this bimodality, this clustering kind of pop up. And if you don't run a clustering, so I run K means clustering on this, and if you analyze what the clusters look like, they essentially look like this. So here is the truth, and the bottom is a truth blurred to geometry resolution. This is one cluster, and this is another cluster. And what you can see is that once you blur the clusters to geometry resolutions, they look the same. But unblurred, you can see that there's a difference between the two. In particular, what happens is that there's this n equals 0 emission, this n equal 1 emission, and the model can't tell which is which. So it has a cluster where the n equals 0 is smaller than n equal 1, and it has a cluster where the n equals 0 is bigger than the n equal 1. So it's kind of important to this debate. Essentially, what that means is that if you did this study and you have reasons to believe that something like this is aphysical, you could cross that out, and then that would leave you with mode 1, but you would incorporate that within your priors. Finally, to the question about fitting to snapshots. So we fit the models to snapshots because we want to fit it to data to see if the variability, the position of variables in the snapshots that we expect there to be in the real data will affect the model fits. And what we can see is that at least at EHT resolutions, they don't affect the fits too much. We did some studies to show that. And lastly, we fit it to EHT data. What we see is that we get a mass that's consistent with the EHT's mass measurement and the stellar mass dynamics measurements. So that helps add some extra footing to the claim that the stellar dynamics mass measurement is correct. We're unable to constrain the spin, and I think this is a sort of an interesting result in itself because what you actually see this happening here as well. If you fit the model to itself under the assumption of EHT resolution, it's unable to constrain the spin, which seems to imply that at least at EHT resolution, even if you know the model perfectly, you will not be able to measure the spin from just intensity measurements alone. You need some additional information in order to do that.
Sorry, I'm just trying to interrupt. We usually allow for interactions with the speaker well into the half an hour after the first hour. So for those of you who absolutely need to leave in the next 3 minutes, please feel free to do so. You're welcome to keep talking if you need some more time. And then those who can stay can interact with the speaker a bit more if they want to. Sorry.
Yeah, I'm about to wrap up. So I just 2 more statements about this. The inclination of the spin axis is consistent with the inclination of large scale jet. So that's interesting, especially given the current or the conversation going on whether the jet axis is precessing or not. But what we do measure is a PA that's not consistent with the actual large scale PA. So this is likely due to model misspecification that we see similar effects happening here when we fit snapshot data. So the way to start to resolve this to see if this is just luck or just a coincidence or just incredibly wrong is to fit further epochs of EHT data. Preliminary stuff, there's BECS going on. I mentioned the photon ring. It seems like at least if you do fits of the model to BECS data, you are able to constrain things like spin and mass fairly well with broadly tight posteriors. And I mentioned before that like the model is very flexible, so we're working on this. This is essentially like a NERF model. It's not really a NERF model because it's not a neural net. It's a Gaussian process, but we're working on this extension of the model that will sort of fit. We're relaxing the axisymmetry assumption where we can fit snapshots hopefully with the model. This is just an example showing. So this is just like an example fit, and these are some instantiations of. They're just random draws of the model. So that's what I have here. Thank you.
Thank you, Don, for a very nice talk. Anyone has any additional comments, questions, points? No, if not, thank you so much and see you guys next week. Thanks.